All right. So today in the second lecture, we are going to be talking about a particular aspect of quantum mechanics that is crucial to how the theory is very different from classical mechanics. So I will talk about this as a thought experiment that was originally formulated by Feynman and others. And as I told you, there is also a beautiful description of this particular experiment in Feynman Lectures, Volume 3. But this experiment has now been done, and we'll also see a small clip of this particular experiment toward the end of this lecture to see strikingly how quantum phenomena do take place in a laboratory. Okay, so the setting for this particular lecture is what you already probably have seen in your high school as the double slit experiment. Okay, so we're going to be doing a double slit experiment with various different kinds of particles. Okay, and we're going to try and understand what the double slit experiment would probably give us when we try and do this experiment with various different kinds of particles. Of course, you have all seen the Young's double slit experiment that was done with light to observe the interference phenomena. We will briefly recapitulate that experiment also in this particular lecture. But we'll be interested to see how this experiment would behave when we do it with particles like electrons. Okay, so let's get started. So what is a double slit experiment? The basic setup is actually very simple. So you have some gun over here. Okay, that is my drawing of a gun, whatever that is, which shoots whatever you want to shoot out. Okay, like this. Now the gun shoots out things democratically, which means it shoots out things at all possible angles here. Okay, so every angle here is equally probable. It doesn't choose a preferred direction, only choose particles this direction or that direction. Okay. All right. So first, let us do this double slit experiment with a classical particles like small marbles. Okay. So small marbles. We are doing this double slit experiment with small marbles. So our gun is a marble gun. It shoots out these marbles at all possible angles. Now in front of the gun, I'm going to place a wall with two slits in it. So I'm going to place a wall over here. Right here. Oops, excuse me. Okay. So I'm going to call this slit as S. Oops. I'm going to call this slit as S1 and this slit as S2. Okay. And behind this screen with two slits in it, I'm going to place a detector. So there is this detector. What does the detector do? The detector, so this is the detector. I should remember to take this off. Okay. The detector detects the particles. So whatever is being shot here finally gets deposited on the detector, and we can see the pattern of deposition. Okay. So let us start doing the double slit experiment. So when I do the double slit experiment with what is basically a classical particle like a marble, what would I expect? Well, the particle, a marble can go straight through slit 1 and hit the detector. Now I'll assume that the screen is strong enough that the marble cannot pierce the screen. So the only way the marble can reach the detector is if it goes through this slit or that slit. So I will assume that these walls are very, very high. Okay. So the only way the marble can reach one of these, this detector is if it goes through one of the slits. Okay. So what would be the pattern of deposition? In other words, now one way to do this is to try and figure out where every marble goes by looking at where tracking each single marble. But as you know, that is actually a very difficult proposition. I can even calculate it theoretically, but that is difficult. when there is lots of different number of particles, classical mechanics gives way to understanding things on a statistical basis. So I can ask for the probability distribution of finding these marbles on the detector. Okay. So suppose if I close slit 2 and simply open slit 1, then all the marbles are going to go through slit 1 and deposit themselves on this detector. So it's obvious that in that case, if I draw the screen right over here, again, the screen, sorry, I'll draw it a little closer over here. My probability distribution is going to look somewhat like this. Yeah. It's going to look somewhat like this, because there is not a very good chance that the particle can go through the slit 1 and end up downward on this detector. So let us call this the z-axis. Okay, so the particle cannot be found in the negative z-axis very effectively. It can only be found in the positive z-axis because it goes through slit 1. Okay, so this probability we will call P1. Now I say probability because this is a probability distribution, because I'm talking about a lot of different number of marbles. But of course, I can actually do the experiment with marbles. Marbles are available to me. I can always construct the slit and I can actually make a graph of the distribution of the marbles on the detector, and I would get exactly what I have drawn here if I close the slit S2. Okay. Now, what happens if I do it by closing the slit S1 and opening the slit S2? I'm going to get something that looks like this. Yes, of course, I mean, my drawing is not very accurate, forgive me, but you sort of understand the picture, right? If I open the slit S2, the particles are going to be found more in the negative z direction. If I assume that this middle line is 0, particles are going to be found in the downward direction, not in the upward direction, because the chances of a particle going through S2 and depositing themselves in the positive z-axis is quite small. Okay, so I will maybe redraw this by repositioning this slit to conform with my okay, somewhat like this. Now, the question that one can ask is, what happens if I open both slits S1 and S2? If I open both slits S1 and S2, as you can probably guess, yeah, only if I open only the slit S1, the maximum occurs somewhat in the positive z direction. If I open only slit S2, the maximum occurs in the negative z direction. But if I open both S1 and S2, the maximum is going to occur in the middle, because the probability will simply add. As you know, classical probabilities simply adds. So the net probability that I will find the billiard ball anywhere on the detector would take a shape like this. Okay, so, oops, excuse me. So this P probability the total probability is just the probability for the marble to go through slit 1 and deposit itself on the detector, plus the probability for the particle to go through slit 2 and deposit itself on the detector. Okay, so this is a very simple classical picture that you can simply do in a lab and confirm. And again, apologize if the figure is not to scale, but I suppose you can get the basic idea of what I'm trying to convey. Okay. So this is how classical particles behave. This is how we expect classical particles to behave. Okay. Both these words are important, classical and particle. Now, what did Thomas Young do? Thomas Young repeated the exact same experiment with waves instead of particles. So we can take the example of any wave. Okay, so I'll take the example of something like, water wave or sound wave or light wave or whatever you do. Again, I'll draw a gun. Okay, that shoots out waves. Okay, and I will position a screen again with two slits in it, S1 and S2. And I will put a detector at the far end. Okay, so this is my slit S1, this is my slit S2, and this is my detector. Okay, all right. So what happens now if I close slit S2, forgive me, close slit S2 and open slit S1. So let me draw those probability distributions over here. Again, if I close slit S2 and open slit S1, the wave can only escape through S1 and deposit itself on the detector here. So I'm going to get a distribution that looks exactly like what you observed before. So let us call this P1 prime. Okay. Similarly, if I close slit S1 and open slit S2, I'm going to get something that looks like this. Okay. So now the natural question is, what happens if I open both slits S1 and S2? Is my probability distribution exactly same as P1 plus P2 like I would expect for a classical particle? And we find that this is not true, and I'm assuming that you know this already. What you instead observe are these very interesting patterns of maxima and minima. Okay, sorry, this is a little unsymmetric. I should probably turn my iPad and draw it, but you sort of get the rough idea of what's happening. Okay, what you observe is that there are points on the detector where there is a lot of intensity that is deposited, and there is points on the detector where there is not a lot of intensity deposited. Okay, now remember that I've gone from counting the number of particles to the intensity of the wave. Okay, this is actually an important distinction because classically we had particles and we had waves and there was nothing in between, right? So when we want to measure particles, we count the number of particles. When we want to measure waves, we calculate the intensity of the wave, right? So how do we define the intensity of the wave? So before we move on, I'm assuming that you have seen this before. In case you have not seen this before, this is the famous Young's double slit experiment that showed that light was indeed a wave that showed interference phenomenon. So what is this phenomenon? I'm sure you know the mathematics, but let me go through it very quickly, just for completeness sake. So how do I understand that if there is a particle, the probability just adds and you get a total probability that is just the sum of these two probabilities? But if it is a wave, you get something very different. You get a combined probability that is clearly not the addition of these two probabilities. Instead, it shows a wave-like character. There is a, sorry, not a wave-like character. It shows maxima and minima, and you have some dark spots and some light spots, bright spots. What's going on? So the way one understands this is by making a fundamental assumption about what is the stuff that is being added. So what does that mean? So let me describe a wave phi1, okay, as a1 e to the I, let us say omega t plus phi1, okay. So based on your knowledge of electromagnetism, this form should not be very surprising to you. But if it is surprising, don't worry about it. It is actually very easy. I'm assuming there is a sinusoidal wave, okay? And A1 is called the amplitude of the wave. And I'm assuming here that the amplitude is a real quantity. I don't have to assume that, but I'll assume it for convenience sake. Omega is the frequency, okay, angular frequency. And phi1 is some phase of the wave. Okay, it depends on phase. Simply means how much the wave is shifted with respect to some reference point. Omega is related to the frequency of the wave by omega equals 2 pi nu. You know this already. So usually we take phi1 to be the real component of this wave, but we can also write it in a complex form like this. In fact, the amplitude also can be written as a complex form, and I can take the real part of the entire thing, but I will not do that. So this is basically a sinusoidal wave with some frequency omega and some phase phi1. The intensity of the wave I1 is described by the absolute square of the wave. But since this is purely in phase e to the I omega t plus phi 1, when I take phi 1 square, which is phi 1 times phi 1 star, this becomes a1 square. That is all. Because phi 1 star has a e to the minus I omega t plus phi 1. So phi 1 times phi 1 star cancels off the e to the I part. So I only get the a1 square part. Now, suppose, so what is happening in this experiment? There are two waves that are being emanated. Yeah. So one from this and one from this. Like this. Yes. And these two waves actually talk to each other. They interfere. Now, when two waves interfere, you get a sum, which is a resultant wave. The resultant wave can be written as the sum of these two waves. So suppose if I have two waves, phi 1 and phi 2, the resultant wave phi is simply the addition of phi 1 and phi 2. Okay. So this is given by a1 e to the I omega t plus phi 1 plus a2 e to the I omega t plus phi 2. Now the omega is the same, but I'm simply adding two different amplitudes A, and I'm also accounting for the fact that the phase difference between the phase between these two waves need not be the same. Okay, the first guy has a phase phi 1, the second guy has a phase phi 2. All right. So what is the intensity of the resultant wave? The intensity of the resultant wave, which is the distribution that you see here, you measure the intensity, which is the height of the wave square, right? Amplitude is basically the height of the wave. So if I draw the wave here, yeah, this is the amplitude of the wave, right? And this is one complete wavelength, the entire thing. So the velocity of the wave is nu times lambda and things like that. Nu is related to omega. The intensity of the added wave is simply phi 1 plus phi 2 quantity square, right? So this would be equal to phi 1 square plus phi 2 square by your laws of complex analysis, because phi 1 and phi 2 are written as complex quantities. This would be equal to phi 1 star phi 2 plus phi 2 star phi 1. And if you work out the mathematics, you will find that the intensity of the resultant wave is a1 square plus a2 square plus 2a1 a2 cosine of phi 2 minus phi 1. Okay. So phi 2 minus phi 1 is the phase difference between the two waves, which we can call as some delta, right? So the intensity of the combined wave I is equal to the intensity of the first guy plus the intensity of the second guy plus 2 times square root of intensity of the first guy times the intensity of the second guy times some delta, which is the phase difference between the two waves. And it is this phase difference that causes this weird or beautiful or strange looking phenomena called interference, because the sum, so this guy can cause the entire thing to either be pushed up or pushed down. Of course, it can never be zero. So that's why there is no particular zero, because these two things are I1 and I2 are manifestly positive definite. But this guy can be both negative and positive, and depending on its strength, you can get places where the intensity is maximum and places where the intensity is minimum, and it gives you this characteristic interference phenomenon. All right. So this is what happens when you do interference experiment with waves, which is very different from the interference experiment with respect to particles, where the probabilities simply add. The probability in the case of classical particles is simply the probability that I can find a particle from slit S1 plus the probability that I can find a particle from slit S2. In the case of waves, the intensity of the distribution that you see in the detector is given by the modulus of the addition of the two waves. Okay. So here the addition proceeds differently. That is the essential difference mathematically between the first step and the second step. In the case of waves, you first add the two waves and then take the square of that guy. And the square of that guy is what you see in the on the screen. All right. So now we can push forward and ask the question, what if you do the same experiment with, let us say, an electron or neutrons or whatever it is. Okay, I will do the exact same experiment with electrons. Well, how would I do it? Again, I would have some kind of a gun, in this case an electron gun, that sprays electrons in all possible directions. Okay, and I will position a screen, and I'll cut out two slits on the screen, S1 and S2, and I will put a detector at the far end. Okay. The detector S1 and S2. And I will do the experiment in exactly the same way I did in the first two cases. I'll first close slit S1 and ask for the probability distribution of the electrons to be found on the detector. If I do that, I would get something that looks like this. Okay, and you're all very happy because this is exactly what we found for both classical particles and classical waves. Suppose if I close slit S2, I would get something like this. Now, if I open both slits S1 and S2, I would expect if electrons were just particles with classical properties and were indistinguishable from something like, billiards balls or anything like that, then I should expect the probabilities to add and I should get a distribution that looks like this, right? Suppose if I do this experiment with electrons, but I don't, okay? Instead, I get something that looks like what you would expect if you were doing an interference experiment with waves. In other words, if I do an experiment with electrons in exactly the same way, the pattern that I see on the detector, that is the probability distribution of the electrons on the detector, actually follows a wave-like pattern. Now, it is important to understand how I'm doing this experiment. Right? How am I doing this experiment? Here, I am not measuring the intensity of electrons. I am actually counting the number of electrons. Yes? So, what I'm doing is that I'm allowing the electrons to pass through either slit S1 or S2, and I have some kind of a detector that counts these electrons. So assume that I have positioned such detectors all along the screen detector, and every time an electron comes and bombards this detector, I hear a click, 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 and either using the number of clicks, I just draw this distribution. Okay, and I find that there is less clicks towards the positive z direction, there is less clicks towards the negative z direction, but between the two extremes, I get an interference pattern, and I find that the number of clicks is maximum at the center. So here is a very interesting phenomena. The electrons do arrive at the detector like the billiards balls arrive. They arrive in classical lumps, right? So tuck, 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 just like a billiard ball would make a sound when you hit it on the detector. So I'm certain that the electron is now a particle, right? It's a particle because I hear these click sounds and they come in discrete intervals. So every time an electron comes and clicks, I hear a sound. So which means I conclude it's a particle. But when I actually look at the distribution of these particles, I actually find a wave-like pattern. So this is the sense in which we say that particles also have wave-like properties. And this is what I was trying to convey in the last lecture also. That when you look at subatomic particles, there is something weird going on, and it's very difficult to establish the properties of electrons using classical physics, classical mechanics. So clearly, if everything was simply classical, I should have gotten a distribution of the electrons that looks just like the P1 plus P2 distribution of the billiards ball, but that is certainly not the case. Okay. Now, just 1 second. It is certainly not. I'm not able to see the screen and when what I'm writing. So just give me 1 second. I'm trying to figure out what's going on. Okay, so since the share screen was not working, so let me take a couple of minutes to answer some of the questions that have come up. In the experiment involving marbles, showed the graph of probability distributions with the superposition of the two graphs observed on the screen instead of having a maxima in the center. So if we actually add the number of marbles that is being stuck on the detector, that is exactly the probability distribution you would get. See, if I close one of the two slits, it is true that the probability distribution is maximum either on the top or the bottom. But if I open both the slits, the overlap between the two graphs in the center becomes large enough that I did not draw it to scale, obviously. The overlap between the two becomes large enough that the maximum is actually at the center and not at the two ends. Okay, so this is something you can actually do and test out. The other question is, it does not make sense for the probability distribution on detector if it is a sum of individual probabilities. Can you please elaborate for the case of marbles? So for the case of marbles, if I open both the slits, obviously the total probability would be the sum of these two probabilities, because the marble definitely goes through either the first slit or the second slit. Now the question is, why does that, maybe my drawing was not very accurate. The question is, why does the sum look like this? The sum does look like this. The only error possibly could be the scale of my drawing. Okay. Sir, your voice is breaking. Okay. So please let me know if my voice is breaking even now. If so, then we'll have to recalibrate. So I will again try to connect to my iPad. This time, hopefully things should work. Let us see. Okay. All right. So now the question is, how do I describe this mathematically, right? The way I would describe this mathematically is as follows. So let me finish this lecture and then take questions at the end. You can keep typing on the message board. Unfortunately, when the screen is on, I don't see the message board, but I will certainly see the message board at the end. So please hold on to your questions and ask me at the end. All right. So this introduces a very important concept that we will be talking about over and over again in our lectures on quantum mechanics. And this concept is the notion of probability amplitude. What does this notion mean? Well, it is clear that since the distribution of the electron, the pattern of distribution of the electron on the detector looks very much like the pattern of interference of two waves, the intensity distribution of the addition of two waves on a detector, the mathematics of addition of two electrons should be somewhat like the mathematics that we described on the page that is visible to you right now, right? Like in two waves. The question is, what waves? Because electron, we just discussed, arrives in discrete lumps. It click, click, click. Each electron arrives. So what is the wave? Well, these are waves of probability, loosely speaking. What does this mean? This means the following. There is a certain probability amplitude that we assign for an electron from slit S1 to deposit itself on the detector. There is a certain probability amplitude that we assign for the electron to go through slit S2 and deposit itself on the detector. Okay, and the net probability amplitude that the electron can be found on the detector is the sum of these two probability amplitudes. The probability amplitudes, just like the case of phi1 and phi2 for waves, is in general a complex quantity. Now, the way to get another total probability is a real quantity, right? Probability should be 0.3, 0.4, 0.1, whatever it is. So the only way to get a real quantity out of a complex quantity is to take the absolute modulus. So we define a probability amplitude for the electron to go from S1 to the detector. Okay, and this probability amplitude we call phi1, or rather, let us call it by a different name. Let's call it psi1. Similarly, the probability amplitude to go from S2 to the detector, we will call psi2. Okay, so the total probability amplitude that the electron can go through either slit S1 or slit S2 to the detector is given by the sum of these two probability amplitudes. And the total probability is modulus of psi square. And since psi1 and psi2 are complex quantities, psi1 plus psi2 modulus square, exactly like phi1 plus phi2 modulus square, will get some kind of an interference pattern simply because there is some kind of an interference term in this addition. So again, what is it that we are adding? We are not claiming that the electron is a wave which is described by psi1, or electron is a wave that is described by psi2. No, that is not what we are saying. What we are saying is basically very simple. We have to assign, since we are shooting lots of electrons, we have to assign a probability that an electron will go through slit 1 and deposit itself to the detector. Now, we can directly calculate this amplitude probability, but quantum mechanics tells you that you have to calculate this probability in two steps. The first step is you have to figure out what is the probability amplitude for the electron to go from S1 to the detector. And then once you have the probability amplitude, you have to take the modulus square of this complex number, and that will give you the probability. This is the quantum mechanical prescription for calculating the probability. So the electron itself, I'm not claiming is some kind of a wave that is described by psi, but I'm claiming that whatever the electron is, whether it's a wave or a particle, whatever it is, the way to assign probabilities to understand how the electron moves follows a quantum mechanical prescription that looks very much like the prescription that one follows in the case of light waves. Okay, the probability amplitude. So you don't add probabilities directly, but you add probability amplitudes, and then you take the absolute square of the probability amplitude, and that gives you the probability. So basically, this is a way to make the mathematics of quantum mechanical particles exactly similar to the mathematics of waves that you see here. Okay, here I'm simply adding two waves, and adding two waves makes sense to you, right? Because I have a wave psi1, I have a wave psi2, and if I add the two waves, I get psi1 plus psi2. There is nothing wrong. So I want to import the exact same simple mathematics. To do that, I assign the notion of a probability amplitude. So every event that happens in the world has a probability amplitude, and the absolute probability that this event will happen is given by the absolute square of the probability amplitude. So here we see, now you might ask, well, what happens if the electrons go there one by one? Should I still assign a probability amplitude? I can simply track the electrons and see what's going on. So this notion of tracking becomes important. So I'll answer the question of what happens if you send the electrons one by one. But before that, I want to answer this is something that I've already told you before in some sense, right? So everything has a wave-like property. But there is another crucial property that you have to understand. So let us do the exact same experiment. Okay, the double slit experiment, till it completely bores us out of our mind. But this time we will make a slight modification. The slight modification that we will make is as follows. So again, we will shoot the electrons from the electron gun, and they keep going everywhere. Okay, and I'll position a screen with two slits, S1 and S2, and I will look at the pattern on the detector. So this is my S1, this is my S2, and this is my detector. Okay. Now I'll make one difference. I'll put in one difference from my previous arrangement. From my previous arrangement, what I will do is I'll place some kind of a light source here. The light source I will use to understand if the electron is going through slit S1 or S2. Okay. Previously, I had no such thing. I did not know whether the electron is going through slit S1 or slit S2. I had no idea, but now I have an idea. Now the electron, I know which electron is going through slit S1, which electron is going through slit S2, because I have a light source here. So if I sufficiently slow down the electron gun, then I can easily track all the electrons, right? Because the electron, the light, it will interact the photon from the light source and get scattered. So I can see these flashes of light that is emanating from S1 and S2 every time an electron passes through S1 or every time an electron passes through S2. And I will do the exact same experiment. I will open S1 and close S2, and I will get the exact same probability distribution as last time. It will be maximum in the positive Z direction. If I close S1, open S2, again it will be the same. Now if I open S1 and S2, I will expect that the pattern would look like what I just observed for the electrons, like here, but I don't. If I open both slits S1 and S2, the pattern becomes billiard balls again. Okay. So this is the total probability. Let's call this P double prime. So again, what is the difference between this setup and the previous setup? In the previous setup, I do not know which slit the electron is coming through. Okay, I am completely oblivious to the fact that the electron is coming through either slit S1 or S2. All I know is I'm counting the electrons that are hitting the detector. In the second case, I'm actually tracking the electrons. They are actually coming from either slit S1 or slit S2. Okay, I know exactly if this electron is coming from slit S1 or from slit S2. Okay, so if I track the electrons, then its pattern does not show an interference pattern. If I don't track the electrons, its pattern shows an interference effect. This is what is at the heart of quantum mechanics, and I will say this again because it is very important. If there is multiple ways an event can happen, the event in this case is basically an electron hitting the detector. In this case, there is two ways this event can happen. It can happen if the electron comes through slit S1 or comes through slit S2. The event itself is the hitting of the electron on the detector, and this event can happen in two different ways. If there is multiple ways in which an event can happen, and I do not know which way it happens a priori, then the way I calculate the probability is assigning an individual probability for everything and simply adding all the all the probability amplitudes and then squaring them, just as I've done on this page. But if I know which slit the electron is coming through, then all this fails. I know exactly which way the electron is coming through. So the probability that I find it hitting the detector is basically psi1 square plus psi2 square. Okay. So there is a fundamental difference between quantum mechanics and classical mechanics in this particular aspect. And this particular aspect is the fact that the observation and the experimenter is intimately tied to what the theory is. So so you must have all heard the famous statement that Einstein said, like, if I don't look at the moon, does it still exist? This is what he was referring to. So if you look and you know which way an experiment, which path the electron is taking, you get one particular interference pattern. And if you don't look and you don't know which way the electron is coming through, and you look at the interference pattern and look at the pattern of the detector, there is an interference pattern. Okay, so the interference is lost if I know precisely which way an event occurs. If I do not know which way an event occurs, then I have to account for the possibility that it can occur through any particular path. Okay. Again, there is a lag, so I'll stop sharing and start sharing again. Forgive me, there is. Okay. Okay. So this is the fundamental difference. This is what is actually really strange about quantum mechanics, that if there is multiple ways in which an event can happen, then whether or not there is an interference depends on the fact that whether you are keeping track of which way the event is happening or not. Okay. So what is the takeaway from this lecture? The takeaway from this lecture is that for every event, for any event to occur, there is a probability amplitude psi. Okay. If there are multiple ways this event can happen, the net psi is the simple addition of all the different ways in which it can happen. And the net probability amplitudes for all the different ways in which it can happen, and the net probability is the modulus square of the net probability amplitude. Okay, it is the net probability is not psi1 square plus psi2 square and so on. It is the absolute modulus of psi square, provided you are not keeping track. Okay, you do not know which we are not measuring if the electron is coming from S1 or S2 or S3. If you are not doing the measurement, if you are not keeping track of the path of the electron, then this is the way you calculate the probability. If you are calculating the path of the electron, then the interference pattern is lost, and it is simply basically psi1 square plus psi2 square. Okay, so this is the net net take-home message of this particular lecture. We will certainly talk more about this. I should also tell you that, of course, the game of quantum mechanics is basically to try and understand what this psi is for every situation. It turns out that this probability amplitude can be gotten from something called the wave function of a system. Unfortunately, I use the same symbol, but the wave function is also denoted by psi. So there is a particular rule that tells you that if you know the wave function for a particular system, you can calculate all these probability amplitudes for all events that can possibly happen. So the fundamental game of quantum mechanics is to try and figure out what is the wave function of a system. But of course, we cannot simply give you the rule. We'll develop this subject in steps. This is the motivation for why you need a wave function, motivation for trying to see why quantum mechanics behaves very differently from classical mechanics. And I'm sure most of you have lots of questions, and we will address all these questions and other questions you will have based on the uploads that I will do today and tomorrow and the next week live discussion sessions. Now I will stop sharing and then look at some of these questions.